big challenges for silicon photonics is to get things aligned so that you can perform the testing and assembly processes that are required to make a finished product. This is an example of one of our fast multi-channel photonic alignment machines. There's two micro robots working on either side of a simulated silicon photonic chip that in this case is composed of single mode fibers in arrays that go in and out, just like a real silicon photonic chip. So in this demonstration we're showing the ability of this technology to rapidly perform the multiple alignments required to get all of the degrees of freedom, all of the channels on the inputs and the outputs of this device all aligned in a single step. It takes about a second to do the actual alignment, and that has been a real enabler for this industry. You have seen this in probers from FormFactor, MPI, probing wafers, the chips that are on the wafer before the packaging process continues. You've also seen these machines are embedded as micro robots into assembly tooling by companies like Etteplan. So this is an example of a specialized micro robot that performs the exacting tasks required to make silicon photonic devices. Over here you see a new technology that addresses the last remaining hurdle for improving photonics manufacturing production economics. Here you can see one of our high-speed mirror mounts steering a blue laser beam, trying to find something. It is performing a repetitive search pattern to try to find a 9 micron core single mode fiber to get the first light through. This is one of the remaining frustrations that photonics customers have, how to get that glimmer of light, that first few photons through a device. Well, watch. See how rapidly it can acquire that single mode fiber. What we've done is we've found that 9 micron core within a search area of a couple of centimeters. This is a new technology, a new algorithm. We call it PI Lightning, and it's built into our controllers. It's the missing piece of our systems here. We've provided fast multi-channel photonic alignment optimization for characterization, for assembly and test, but finding that first light has been left as an exercise for the user. Well, now we've taken this and we've made it into a fully parallelized technology that can perform this rapid acquisition on both sides of a waveguide, if you wish. Here you can see the PI Lightning technology applied to photonics. We have 2 single mode fibers. Same challenge. Try to get them so that the first few photons get through, so that the rest of the alignment process and the optimization process can proceed. So as you can see, it's screamingly fast to find the first light for these 2 fibers when they're placed in close proximity to each other. So again, this is one of the frustrations, or has been one of the frustrations that customers have had, trying to find that first photon or 2 to get through a silicon photonic device or other coupling situation. This is the problem that PI has solved. Here we have something which is optically very similar to many silicon photonic chips. We have an input and an output, and they're connected together. And you have to find, the challenge is to find first light, to get the light through both of those at the same time. So, watch this. We put this, it's done. It takes tens of milliseconds to get the first light captured between these 2 couplings so that light goes all the way through. And anyone who has worked with fiber optics knows that that is a painful problem to solve. You can do it manually, it just takes a long time. As you can see, we've taken that process and we've turned it into something that takes perhaps a few tens of milliseconds, which is an immense savings of time. And that's really what it's all about. That is PI's role in the silicon photonics market, is finding those pain points that affect production economics for our customers and get rid of them. That's what we've done with our FMPA solution, and now we have expanded and extended that to solve the first light challenge. I'm Scott Jordan from PI. Thank you for watching.